Hi and welcome to the lesson about data stores. So data stores are maybe a side effect of data processing because each data processing job generates some output and materializes it somewhere, and this somewhere happens to be these data stores discussed in this lesson. So I bet that you're already asking yourself, hey, what is the best data store to use in data architecture? So the problem is that there is no one. The answer it's maybe the favorite answer of each consultant. It depends. So it depends on various requirements. So for example, like latency. If you have low latency requirement, you may be better with in-memory data stores, backed of course with some persistence layer, but still their data is accessed from memory. Maybe if you need some distributed data processing at scale, then object stores are maybe better fit for you. If you are requiring some streaming data, then streaming brokers are maybe better than publish subscribe message queues and stuff like that. So always you have to ask yourself what I want, and depending on the answer, choose the corresponding data store. But in this lesson, we are going to see different data stores, and each time I will try to give you some pros and cons so that you can choose the good one to your need. So the first system is maybe something that you already know. It's quite popular among backend developers, even front-end software engineers know something about relational databases. And in a nutshell, we can describe its architecture like that. We have tables and other objects, like for example stored procedures or maybe some functions that are stored in pages, and each page is composed from page header and rows. And additionally, we have the index to optimize the data access. And the specificity of relational database management systems is strong consistency, meaning that if the write succeeds, it means that it will be there forever, and the structure helping to achieve that is called a write ahead log, because each operation goes first to the wall and later it's only materialized on the pages. So in a summary, we have one database that can have multiple tables, and each table might have one or multiple rows, or even zero if it's a fresh table. The second interesting point is about the structure. So each table has a schema, meaning that there is a static structure of the data, which is good to know what type of fields you have, maybe what are thanks to the constraints, you may also know what are the expected values and things like that. And additionally to that, you can also create relationships between tables so that optimize, for example, the joins, or maybe do some cascading work where, for example, you have a parent table and you delete a row from this parent table. You can use cascade delete to remove the row with the same key from the children tables. So it's also a very powerful feature. So normalized data, as I said before, because thanks to these relationships and structure, you can create a data which is very normalized, that doesn't repeat, and of course it's much more efficient for the storage. And also indexes, as I mentioned before, it's something that you can add on top of each table to optimize the access. Of course, remember the trade-off, each index must be written, so if you add an index, it means that your write will be obviously slower, because in addition to writing data to the page, you will also need to update the index. ACID, which is a strong guarantee of atomicity, consistency, isolation, and durability, meaning that there is no partial data that will be written. Partial data might be read if you decide to use a weak level of transaction isolation, but anyway, it's something that it's not, I think, very often used in relational database management systems, because they are very famous for consistent reads and isolated transactions. And SQL, SQL is the key language for relational databases. And to scale the reads, you can add Red Replica. So Red Replica will generally be a server pulling the data from the writer node, and it will be available for the consumers to do some select statements, but it will not be writable. So generally, you can see already that we can scale readers quite easily, but it's not necessarily the case for the writers because there is always one that is in front of the producers. And to sum up the pros and cons, so RDBMS is good for transactional workloads because because of this ACID guarantee, and it's bad for the workloads that need some scaling because, as you saw, all reads and writes always go to the single node, unless you do some more complex operations like sharding. But yeah, it's something that exists. But if you need some scaling, maybe you will use different solution like for example, columnar file formats in object store or distributed file system. And yeah, that's also something I have mentioned just before. Analytical queries will be more efficient in a different storage format because here you have rows. So whenever you need one specific column, you always need to access the whole row. Whereas if you use columnar storage format, then you can correctly isolate and target one specific column. The second type of data stores are NoSQL data stores, so not only SQL, and they are usually much more scalable, but they don't provide the same ACID guarantees, and they are not very suited for normalized data, meaning that you might need to denormalize it a bit. And the first type are key value data stores. So key value data stores identifies each row by key, a little bit like primary keys in relational database, and they put the rest of the information as a value. So now your query must know exactly the key that is needed, because otherwise it cannot correctly target the data. So the key-based access, later we have kind of distributed map of different values, and IDEP, it's maybe something that you will often use to implement the writing idempotency, because if you are capable of generating the same key for the job, if you process given record, then each write on your key value store will always end up with a single row written. And among the goods, so yeah, you have some direct lookups needs. There is very fast to access by key, and there is no overhead of creating an index or something like that, as you can have in relational databases. Idempotency is other point. And among the bad ones, yeah, ad hoc queries, if you don't know the key, it will be very difficult to query and to use the key value data store. And of course, normalized data storage, because imagine that you have two NoSQL tables and one user might have different addresses, so you cannot do the join as you could do in relational database. Instead, you would need to read first your users table, get all user keys, and later do the reads on your addresses table, which obviously will be less efficient than doing that in a single process in relational database. Next is quite similar solution, always identifies data by key, but here we are talking about column family, so the groups of attributes that are stored together. So if, for example, you are going to read all attributes of the same column family, it should be much faster to do. And of course, query, again, it uses primary key, so this key identifying the row, but you can additionally extend it with sort key. Sort key is something that lets you store different values for the same primary key in the table and store them by the value in the sort key. For example, we can imagine a web logging table that stores all times when a user logged to your service, and you can have user ID as a key and a login timestamp as an sort key. So still there is key-based access. With sorting key, you can have different combinations. There's column family grouping all these related attributes together, and it's good for query with subset of attributes, because you can see that it's much more optimized with this column family thing. A schema can be variable. That's also something that's much more important. Schema cannot be variable in relational databases. Here you have the possibility to add different values. So you can see already in my user B that I have only one value for each column family. I don't need to have different values. Of course, you can do that on SQL too, but there is there is less efficient storage for that. And among the bad things, yeah, ad hoc queries are not good too, because you need to know the key, and also there is no ACID strong consistency, because here generally the transaction is, or the consistency is limited to each row. You will not get it across different rows written, and it's something that happens, for example, while you are writing 10 rows, maybe the first one will succeed, they will be in the new state, and the 5 remaining ones will be in the old previous state. So the transaction will be partially succeeded, even though technically we don't talk about transactions. And also we have other data NoSQL data stores. First is document data store. Here also we are accessing data by key, but instead of storing attributes or a value, we are storing a JSON document in the value. And the good point here is that it's even more schemaless, because you can store documents with completely different things inside, and of course it has some other implications. But anyway, yeah, unit storage is a document. It can be, you can have collection of documents corresponding to each row. There is schemaless, really schemaless per se, because a document can have different schemas. And the good thing is that if you need some fast access, you can define some indexes on top of these document fields. Of course, if you have very disparate documents, it will not help at all. It will help a little, but still you might be lost in the end, so it may be better to create different tables or do some reconciliation among the documents. And the good point for that is, if you need semi-structured data, maybe there is nothing better than that. And among the bad things, of course, it's the opposite. If you need some structure or normalization, yeah, it will not be very easy to do in case of document data stores. And a specialization of document data stores are search engines. So search engine is composed of an inverted index. So the index that, depending on your rules, will take maybe the first X letters from a word and define a list of matching documents. So for example, we can imagine that we want to index a document by an attribute called word. And this word can be different. We have Canada in the other documents, and you can already see that depending on the format of the index. So we defined an index starting from four letters. Sorry, we can have different documents corresponding to it. So for example, now if your user searches for Canada, it will get 4 documents. But if the user knows that he or she is looking for Canada, then he or she will get only these specific documents. So it's document based. There is this inverted index as a key for the whole system, and it's good for any exact approximate matching. As you saw, we have different words in the index key, and we can match various corresponding documents. And it's bad for write intensive workloads, because you can see, depending on the complexity of the key, there are one or multiple places to update, exactly as a drawback for relational databases with the optional indexes on each table. And in NoSQL category, you will also find graph databases that can have different representations. So the first representation is based on kind of adjacency representation, where you kind of materialize the graph in the file. And the other one is by using the matrix that is often backed by key value stores you saw previously, when you can define 1 when vertex and edge are connected, and -1 when there is no connection at all between them. So a graph is a set of vertices and edges. It's very good if you need some deep traversals. Eventually you can do them also with SQL, but if you don't know the deep, it may be very complicated to write all these joins, self joins between in the table. And besides writing complexity, the self joins can be also much less efficient than doing this traversal, for example, in this adjacency representation. But the drawback is that if you represent data in this format, it will be often a single node representation. So obviously, as a relational database is less scalable in reading and distributed processing, and also you could mitigate that with some optional index, but still it may not be efficient in fact. But anyway, yeah, as I said, deep traversals, there is maybe nothing better than graph database, but on the other hand, if you have direct or maybe unitary access on the graph, there may be doing some kind of dematerialization and transforming the graph into a key value store, or these subgraphs into a key value store may be much more efficient. And of course, due to this single no character, it can be quite hard to horizontally scale it. Now we are going to talk more so the NoSQLs, relational databases. I bet that there are things that you could encounter if you have working before as a software backend engineer, but data warehouse is something really data specific. It's more the domain of data engineer. So data warehouse is kind of relational database in columnar storage on steroids because it's distributed. So let me just describe the architecture. We have the control node, which is in the control layer. Later we have a communication layer. So each command will go through that and it will reach compute nodes. So compute nodes are located in compute layer, and they will be responsible, for going into the storage layer. Go really look for the data is defined, is looked for by the query, and getting it back as a result. It is very efficient because the storage layer uses a columnar storage, which is very well adapted for analytical queries that very often require only a few rows, a few columns of the whole schema, and is much more efficient to read few rows rather than few columns rather than read all rows and pick only these columns after serialization, like it would happen for relational database. So column-oriented storage, and among the good points, analytical queries, nothing better. But on the other hand, it's less efficient for transactional workloads because, as you can see, all is distributed, and these columns also require some extra work. Like there is also the extra work that speeds up the analytical queries, in fact, but it's still an extra work. And I'm mentioning here, for example, the statistics. So for each column family, each column in the schema, you can have different statistics, and so mean and max values. And now exactly where the rows for each column you are looking for in the query are stored physically on disk. And now we are going to talk more about data in motion. So the first class, I would say, first class data store for data in motion are streaming brokers. So streaming brokers are like an append-only distributed logs where each consumer is independent. So we can have two consumers, and the first one may be at these positions, and the second one can be processing the last rows, and it's an append-only log because now the new data is added in the end of each partition. Because as a total unit of the data, as we could talk about tables in relational databases, in stream brokers we have topics or streams, and each stream or topic has partitions or shards. So the point is that the consumers are isolated, and also if a consumer needs to go back because maybe it made a mistake in the job, you can do this by seeking exactly the position you want. But there is no overall guarantee over on this architecture. The ordering guarantee you might have will always be located in the partition at the partition level. So do not expect that the producer will write some data and your one consumer, even if it processes all the partitions, it will get the records in order. It will get the records in order only inside each partition or shard, depending on the solution. And the streaming broker is good for distributed processing. As you see already, there is a native partitioning. It can be a source of truth for data systems, so you can have different consumers reading data and writing to other data stores. It also is scalable, but on the other hand, it's difficult. But it's something that has been worked on recently and exists, for example, in Apache Kafka with transactions. But it's very hard to achieve this exactly once delivery, because generally it's a log, so you add an entry. There is no way to identify it somehow. So it could be very easy to do with, for example, key value stores. But anyway, it's a drawback, but maybe not will be the drawback for using it in your solution. As an alternative, for me, less scalable are publish subscribe message queues, when there is one consumer and each message once consumed disappears for this consumer and is forgotten. So it's up to the consumer to define the messages to read. There is no persistence because the message is lost, even though I think there is some configuration you can add on different message queues, but anyway, by default there will not be persistence. And it's good for low volumes of data. The reverse semantic is easier. The consumers can be quite flexible because you can also define kind of keys on the messages that you want to process in each consumer, and it's not very good for write intensive workloads. So for big data workloads, reprocessable pipelines, if you don't have this replay possibility, and that's quite much all for this solution. So now there are also more file-based data stores, like block-based storage in a distributed file system, when we have a control plane that knows where each part of data is located, so on which node. You can see here that we have 3 different files by the colors, and each file is replicated on 2 different nodes, and that's why we are talking about distributed file system. A classic example of distributed file system is DFS from Hadoop framework. These access commands are the same as for local systems. So if you do ls, it will list files. If you do cp, it will copy it. You can also do cat to see a part of the file. So it's very similar, of course, with different API behind, but still it should be familiar to do. It's fault tolerant because if one of the nodes go down, the data is still there located on other ones. And of course, by definition is distributed. By definition, to achieve this fault tolerance, the storage is distributed. So it's good for if you have multiple clients, because one client can read the files from this node, another from this node, and they can mix and share the workload and not overload one node with the queries. The data is highly available because of this replication. However, it's very not possible to do the in-place changes. So if you imagine a query like update my data set x equal a or something, it may not be very efficient to do by definition with on top of data processing distributed file systems, because of this distributed character and big data it's supposed to store. Even though I know there are specific formats that support these operations, like Delta Lake, Apache Iceberg, or Apache Hudi. And there is another problem of small files, because the control plane remembers all files locations. So bigger files there is less things to remember and there is less memory pressure. And on the other hand, if you have multiple small files, then obviously the control plane will need much more memory and do much more organizational work to keep all things updated. And as an alternative to them, which is very popular nowadays on the cloud, is our object stores. So object store is not a distributed file system, block-oriented distributed file system. Why? Simply because when you give some directory location to the files, like for example here we have data shapes circle like circle.jpg, then the data will be not stored in data shapes circle-like directories. So if you want to read only circle-like files, you will not be able to go into this subdirectory directly. Instead, this ID, even though it looks like a subdirectory tree, it's a single value. So it's like all is stored in root. You can, to better illustrate that, we can imagine that we are storing the ID in a key value store, and the value is the circle object file. Sorry. So yeah, it's less efficient than distributed file system when it comes from accessing data from these parts. However, it's simple and scales quite well, and with cloud services, it's a choice by default for me to use for big data storage and files. So as I said, popularized with the cloud. The objects are immutable, so you cannot, for example, change a row in the middle of each file. You will always need to get the file first, manipulate it, and write with the same name. The flat organization, so it's not a file system, it's an object store. Good points, this very well suited for distributed data processing and for unstructured data, but on the other hand, it's not a file system, so some of the operations you may think are fast, like listing, may be slower than for a distributed file system. And now, before I finish this long lesson, I'm aware it's a long lesson, but I think that you have now a good idea of all data stores you might have in data systems. And before I finish this long list, I will just mention an extra thing. It's not a pure data store because it doesn't store the data, but it gives you access to the data. And this not data store thing are APIs. So API is a protocol endpoint that can be queried with some parameters, and it's very hard to define what parameters because it always depends on the endpoint, and behind it can be kind of single entry point to data stored in multiple data bases and returning them to the user. So here you can see that we have an object store and a key value store that I reconciliated for a single query and return to the user. So yeah, it can be a good facade proxy to access more than one data store. The whole logic is hidden in this API endpoint, so probably it might be your data team to work on it, but also maybe some backend engineers. And there is control less, meaning that you are limited not by the data store, but you are limited by the API endpoint and the parameters it can accept. So you don't have the full control over the queries and data you can do on the data stores that are behind. But on the other hand, it's flexible, so you can imagine that you don't have this API endpoint and you have to get data from these two places. So you have a job, you have manually target the data you want from the object store. You have to manually target the data from the key value store. Whereas here you have a single entry point you call the API, and it does the job for you, returns the results you want. So it's good for complex data retrieval, as here we have different data stores. Unknown data store, because you can imagine an endpoint, you are doing some experimentation, and if you decide that, for example, you don't want to use object store but you want to use key value store instead, you don't need to change your jobs because they will single access this data store throughout via this API, single API endpoint, and all you need to do is just to change the backend which is behind. But of course, if you need a single data retrieval, you have one data store, yeah, there's no reason to use an HTTP based API at this complexity to your system. So as I said, the lesson was quite long, but I hope that by now you understand what are the data stores in data systems, what are the best data stores for different use cases, and you will consequently you will be able to choose them accordingly to the situation, to the data read to the data readers. So that's something I didn't mention before, but to simplify the decision making, you can use a one trick and think about who will read your data. So if you need an ad hoc queries, you already can eliminate key value stores, you can eliminate columnar families, you can eliminate graph databases. But on the other hand, if you know that you will need to do approximate search, then maybe you already know that there is maybe nothing better than a search engine. So yeah, define always this in function regarding to your data readers. It will simplify your life a lot, even though always, of course, keep in mind the global picture of your system. Thanks for watching and see you in the next lesson.